I am Venubalaji. I am technical assistant to Professor Debrati Sen. Today's tutorial is on MATLAB code for BER generation of BPSK system over AWGN channel. This is the block diagram for BPSK transceiver including AWGN channel. First of all, the modulating data source will be there, where the transmitted data is given to BPSK modulator. BPSK modulator does the BPSK modulation. BPSK modulator first converts the data bits to bipolar signals. That means 0 will be transmitted to -1 and 1 will be mapped to +1. This logic depends upon your implementation. Then after that, each this bipolar transmitted signal will be transmitted over the carrier into the channel. Channel here we are considering as AWGN channel. AWGN channel means additive white Gaussian noise channel. So here additive white Gaussian noise means the noise here additive white Gaussian additive means here the noise will be the channel will be adding noise in additive nature, and white means this channel doesn't account for any non-linearity in the channel or dispersion, and it doesn't introduce any multipath components into the channel. It treats all it provides same power over all frequencies. That means if you look at in this one, in frequency domain, it will be like flat feed. It will be like flat over all frequencies. You can consider this channel as flat feeding channel, and the noise whatever is inherent in the channel will be Gaussian noise. Gaussian, or you can call it as normalized distribution. The channel consists of many noise sources like black body radiation from Earth, and thermal noise introduced by the electronic components, and many other sources will be there. But according to central limit theorem of probability theory, when you include all the noise, when you have so many random variables, when you take the summation of all the random variables, their probability distribution will be like convolution among the probability distribution of all the random variables will be convolved, and finally it will produce Gaussian distribution. So that's why the noise that is present in the additive white this AWGN channel is nothing but Gaussian noise or normalized distribution. Then after the then if you look the free this is in flat feed in frequency domain, in frequency domain the power of the channel is same over all frequencies. That means it is flat feeding channel. If you consider this one in frequency domain, in time domain it will be like impulse kind of response. Gaussian noise will be like this is time domain nature. Channel is nothing but it's like a filter with some tapping with some coefficients. Here if you look at in time domain, the time domain response of channel is nothing but one filter tap coefficients. If you convolve this channel response with the transmitted BPSK signal, it will be like here if you consider this one as y equal to h convolution with, suppose x is nothing but transmitted signal, then Here H will be like impulse kind of channel behavior. So this will give you to the output of the channel is nothing but convolution of impulse response with anything is nothing but the same signal you will get. That means here output of the AWGN signal is nothing, AWGN channel is nothing but the transmitted BPSK signal, or noise gets added. So the transmitted signal with the addition of noise will be given to BPSK demodulator. BPSK demodulator does the demodulation, and then we will get the detected bits. This is the BPSK constellation. BPSK constellation, in BPSK, as we are transmitting 0 and 1 bits, one is mapped here, 1 is mapped to +1 and 0 is mapped to -1. So if you draw the constellation diagram of this BPSK diagram, it will be like +1 will be having energy of square root of EB, where EB is the energy per bit. This minus square root of EB is the energy per transmitted -1, means corresponding to 0. It will be like minus square root of EB. Both the transmitted bits are separated by 180 degrees phase shift. This will be like 0 degrees and this is 180 degrees, and the distance between the constellation points is 2 into square root of EB. This BPSK modulation is more robust to the amount of noise required or the amount of distortion required to make the system unable to detect the bits. That means you require very big amount of noise or distortion required to move the signal points to this side, so that you cannot detect. That means if the distance between the signal points becomes less, that means when the signal points come closer to each other, then you will not be able to detect the signal. But here in the case of BPSK signal, BPSK modulation, you are having the maximum distance between the signal points, so that you need a very high amount of noise introduction in the system, so that you will not be able to detect the bits, which will not be generally feasible. That's why BPSK system is more robust to the any amount of distortion introduced in the channel. This is the now I am going to tell about the generation of BPSK, BR generation for BPSK over AWGN channel. First I am considering here 10 to the power of 6 number of bits to be transmitted. Next here I am going to plot BER with respect to this is probability of error, or you can say this is bit error, means how many number of bits are in error over the transmitted number of bits. Suppose I have transmitted 10 power 6 bits, means suppose if 10 bits are in error, 10 by 10 power 6 means bit error will be around 10 power minus 5 plotted against EB by N0 in dB. So generally it will come like monotonically decreasing function. This thing I am going to simulate with the help of this MATLAB code. So number of bits transmitted are 10 power 6, and EB by N0 is taken in dB scale, and I am taking from minus 4 dB to 10 dB over an increment of 2. Next I am generating the I have written a logic to convert, to map 1 to +1 and 1 to -1. So for that I have taken a distribution called RAND. RAND is a uniform distribution. RAND is a uniform distribution generation. Like it will generate the bits between, it will generate the random numbers which follows uniform distribution between 0 to 1. If the generated and if how many number of bits you want to generate randomly, that many number of bits you can pass as an argument to the RAND function. Suppose you are generating, you are passing RAND of 1 comma 10 power 6 bits. That means it will generate 1 into 10 power 6 number of bits like this, and each one will be varying from 0 to 1, means it can be 0.2, it can be 0.8 like this, but they are within the limits of 0 to 1. So that if the randomly distributed numbers are greater than 0.5, that means I am taking here 0.5 as a threshold. So if the generated number is greater than 0.5, then it will be considered as 1, then it is multiplied by 2 and then subtracted 1, means 1 is mapped to 1. If it is less than 0.5 means then it is considered as 0, 2 into 0, 0, 0 minus 1, minus 1. In that way I am generating I am generating bipolar sequence from the transmitted number of bits. Next, this generated bipolar sequence, for this bipolar transmitted sequence I am calculating the power here. I have taken the this transmitted data will be a sequence of 1 and plus 1 and minus 1s. So I am taking the absolute value of those that sequence of plus 1 and minus 1s. Absolute value of plus 1 or minus 1 will be like absolute value of 1 will be 1, absolute value of minus 1 will be minus 1. If it is complex number, then you will get complex magnitude, and I am squaring them. That means I am calculating the energy of each bit. Then I am summing all of the energies. I am summing the energy of all the bits. Then I am dividing by total number of bits. That means 10 power 6. That will give me the power of the transmitted data. Now I am, as I mentioned earlier, I am going to plot bit error with respect to EB by N naught. So that's why I am going to vary EB by N naught regularly. For that I am going to run a loop of for loop with respect to the length of EB by N naught. That's what I mentioned here. A for loop I am running from 1 to length of EB by N naught in dB scale. Next I am converting EB by N naught in dB to the linear scale. As you know, suppose x is in dB, it will be like it can be written as 10 log x of linear to the base 10. That means x linear can be written as x dB by 10 to the power of x dB by 10. That's what happening here. EB by N naught linear is nothing but 10 to the power of EB by N naught dB of each element divided by 10. Next I am generating noise. For generating noise inherently present in any channel is generally complex noise. So to generate complex noise, I am considering a random distribution. Random distribution, as I mentioned, the noise present in the channel is Gaussian noise. Gaussian noise are normally distributed noise that can be generated by using a random function. Here you have to pass the arguments of the length of the transmitted data, so that length of the the generated noise and your transmitted bits will be of the same length. That means the frequency of the transmitted data and the that means bandwidth of the transmitted data and bandwidth of the noise will be same. here I am generating the complex noise, then I am scaling with power of the transmitted data and EB by N0 in linear scale. That will give me the noise. Then noise, as I told you earlier, y equal to h conjugate x, sorry, h convolution x plus n. Here h is impulse response, that will me give the transmitted data plus noise. So that's what I am doing here. Here received data is nothing but transmitted data plus noise. This received data is given to the BPSK demodulator. BPSK demodulator will be having some threshold in order to detect the bits. So here, if the received data is greater than 0, that means if the received data is greater than 0, I am multiplying with 2 and 1. That means if the received data is plus 1, 2 into 1 minus 1 will give me the 1. If the received data is less than 0, means if the received data is greater than 0, then only it will give me 1. If received data is not greater than 0, then it will return 0. Then 2 into 0 minus 1 will give me minus 1. In that way, by keeping a threshold of 0, I am able to demap the signals. I am able to detect the signals. This is decoded signal. This decoded signal then again compared with the transmitted data. If both the transmitted data and the decoded signal are same, then that will give me the 0 output. Otherwise, it will give me the output 1. Then suppose here I am transmitting 1 minus 1 1. Here I am receiving 1 plus 1. Then by comparing with this inequality operator, this will give me the output of 0 1 1, and I am summing all of them. Then it will be 0. Then after summation, this will be equal to 1. That means total number of bits that are in error is 1. Similarly, as we are comparing those 10 power 6 transmitted bits and the decoded signal over AWGN channel, and I am summing all of the bits, that will give me the probability of error in AWGN channel. So I am dividing with the total number of bits. Total number of bits means 10 power 6. This will give me the probability of error over AWGN channel with respect to simulation. This simulation will be run for different number of, as I am running for loop for different number of EB by N naughts. So this will give me the probability of error with respect to each EB by N naught. Next, this is with respect to this is simulated probability of error. Next I am calculating probability of error of BPSK system over AWGN channel theoretically. Theoretically, it follows 1 by 2 into error complementary. This is probability of error theoretically is 1 by 2 into ERFC of square root of EB by N naught. So I am implementing that here. This will give me the probability of error theoretically. Then I am going to plot both probability of error in simulation and probability of error theoretically on semilog y using semilog y command. This semilog y command will generate a plot by taking this x component, and it plots graph with respect to x component and y component. Y component will be taken in logarithmic mode. So probability of error means here y component is probability of error. This will be taken in logarithmic mode. So it will plot probability of error in simulation mode, and I am holding the graph. Then I am plotting the graph with respect to then I am plotting the graph of BR with respect to theoretical. These are like X label you have to mention what you are taking on the X label and Y label. Then legend means legend means at the corner. Generally, if you don't mention the position of the legend, generally it will be like northeast. It will mention what you have plotted. Here I am plotting simulated and theoretical probability of errors that will be listed with respect to color in the legend box. Then you have to mention the title. Then in order to make the grid on, you have to give this command, grid on command. This is the BER plot that we got after running that MATLAB code. This is the BER. The BER means probability of error on y axis, x axis EB by N naught in dB. As you see, over AWGN channel, the simulated the probability of error that we simulated over the AWGN channel and theoretical probability of error over AWGN channel are almost same. That means this graph you can evaluate like this. To generate a probability of 10 power minus 1, you require this one, 10 power minus 1, you have to supply at least minus 1 dB. Sorry. To generate a probability of 10 power minus 1, your required EB by N naught should be minus 1 dB. To generate a probability of error of 10 power minus 2, you require EB by N naught of 3 dB, something like that. And the only difference comes as the EB by N naught increases. Means if you want to generate, this is like as you are going from top to bottom along the y axis, the BER gets decreases. That means out of 10 power 6 bits, here if you take probability of error as 10 power minus 5, that means out of 10 power 6 transmitted bits, only 1 bit is in error. Sorry, 10 bits are in error. 10 by 10 power 6, that means 1 by 10 power 5, that means 10 power minus 5. That means out of transmitted 10 power 6 bits, only 10 bits are in error. To generate that probability of error, you need an EB by N naught, you require an EB by N naught of around some 9.4 or 5, something like that. In the case of theoretical mode. In the case of simulation, there will be, you need an extra addition of 0.4 or 0.5 dB extra. Means there will be a mismatch between simulated probability of error and theoretical probability of error. You can say always theoretical theoretical calculations are much more accurate than the simulated. That's what we observe in the generated graph.